Hey class, so I'm gonna try to be quick and keep it brief again, and it looks like you will not be getting your next homework until next Tuesday. So I got several complaints on that last year, but hopefully this class is a little more forgiving and only having like I don't know 7 or 8 or somewhere between 6 and 10 homework assignments for the semester. But we'll see what we end up with. Anyway. So I hope everyone's exams are going well. A few people have reached out to me to ask questions, and certainly if you have any questions at this point and you feel I can help you, definitely reach out. I'll try and check a few more times before the end of the evening, and hopefully I can get back to you. Okay, and again, I want to clarify that it's not strictly required that you use LaTeX to type up your homework. That's not a requirement because it's not a requirement in any of the course sections, which is why I offer the bonus for it for any students that that put in that additional effort. I'm definitely happy to reward that. Okay, so let's finish up graphs. We'll spend a good deal of time talking about Dijkstra's algorithm, and I will include that with the link to this video. And you can review that, and I will give you some information on your next exam as well. Okay, let's jump into that. Okay, so we ended on non-separable graphs, and basically this is something, you can think of it as a resilient network topology, or a network that is set up that can withstand failure. It's fault tolerant. And so if you think of a network in terms of like an electrical grid, right? So the smart grid that everyone's been asking for a decade or however long, it's essentially what they're looking for is something that's on par with network topology. So you can devise it so that the power stations and the substations all are connected. They are connected in the same way that you would set up a network, so that if you removed one substation or whatever, it automatically fell back on some reserve power source. So that's what they're looking for. If any of you go down that route, this is something to keep in mind, that it does apply to even more than the concept of roads and computer networks. You can also consider electrical grids as a form of a graph, and whenever you're discussing cut vertices and redundancy and fault tolerance and stuff like that, you can also imagine it as applying to that other concept. Okay, connectedness. So we have this new notation, kappa of G. So the connectedness of the graph G is the measure of how many such power stations or substations you would have to take out before whatever neighborhood loses electricity, right? Or before you have one neighborhood that is without electricity, or before you have one block of internet consumers without internet, right? So that is the connectedness of the graph, is how many vertices you can remove before people lose internet. And so in a home network, the router, everything, you lose connectedness as soon as you remove the router. But it's possible that in a setup like a school or something like that, that there would be a little more redundancy, and that perhaps the wireless connection passes through a different route than a hardwired connection, so that if you took out one router, you wouldn't necessarily be depriving the individual, or if you consider that individuals can tether to a network, to a phone network or a wireless network through their phone, and use that as a wireless access point, then they would be two connected, right? So they would have the wireless network for the school, and then if that failed, they could fall back on their phone, right? And so it's just, you know, this is just the measure of how many, different vertices you have to remove before you start getting disconnected or multiple connected components, or distinct disparate graphs or subgraphs or whatever, right, where there's no connection between them. Okay. So strongly connected. This is okay. So now we switch to the context of a directed graph. So the one with arrows, right, as opposed to no arrows. So a directed graph is considered strongly connected if there's a path from A to B and from B to A whenever A and B are vertices in the graph. Okay. So going with the network analogy again, then it would be connected if any two users on the network are able to share files with another, to initiate a file transfer. Right? And so this is not the case whenever one of the devices on the network is hidden behind a firewall. So whenever we were discussing networks earlier, I was saying that it's possible to configure your IP tables or whatever to drop all inbound network requests, anything that isn't initiated by the device itself. And so that's essentially what happens, what routers do automatically for you. So they assume that the average person doesn't know a whole lot about configuring a network and protecting their home computer. And so by default, they will drop any inbound connection requests, and they only let pass responses, like TCP/IP responses, to requests that had previously been made from something within the network, right? And so what that means is that you can't host, by default, using the default configuration of a router, you can't host your own web server in your home. Like you have to, you would have to configure a router to allow that to happen. But in addition to that, it's very likely that your internet service provider will also block inbound requests on port 80, which is the typical one for HTTP requests, so unencrypted traffic. I believe port 443 is the one for HTTPS, and then I think 22 is SSH, but I would have to verify that. Anyway, and so there's these special ports that are specified that requests will come in and they're denied. And so what I'm saying is that in those cases where it's not possible to go back, then it's not a strongly, it doesn't meet this requirement. And so it's one directional. Like you can move out, or you can send traffic out and handle responses or whatever, but you can't accept it coming back in, right? So it doesn't meet that requirement. Okay, and so it's weakly connected if everything, if there's a path between any two vertices, right? But here, for strongly connected, it says that you can initiate it from either A or B, right? But here we don't really care, right? So this is the internet at large is weakly connected in that all of the consumer devices, so everyone's home computer that sits behind a firewall is able to reach everything that's on the wider area network, but not accept requests coming in from other places by default. There are certain workarounds, and any curious individual can reach out to me and ask, but by default you wouldn't be able to, right? And so okay, so the example I give here, and I'm not terribly sure this is necessarily an appropriate example, and so say that a radio broadcast where you're sending the signal out from some source and you're reaching the individuals with radios, that would be an example of being connected, but the radio isn't sending anything back to the tower. But I think this this example of a radio station is even weaker than something that is weakly connected, right? Because there doesn't necessarily exist a path from two radio listeners, right? Like they can't reach each other. The tower can get to them, but there's no path from one to the other because they're going against the order of connection. So just ignore this example. I'll move it at some future iteration of the notes. Okay. So we have a theory here, a graph with adjacency matrix A, right? And we have the vertices numbered from 1 to n, and then we have directed or undirected edges, or edges with multiple loops or whatever. We make no restriction on that. So the number of different paths of length r running from some vertex I to another vertex j, where r is a positive integer, equals the ijth entry of a to the r. Right, so this is kind of a profound statement here. So we're saying that the adjacency matrix is more than just some assistant to represent the graph. Like it actually provides some mathematical basis in that if you multiply it by itself r times, where r is the length, right, then it'll tell you the number of different ways that you can arrive from this source to this destination path. And so I think that's a pretty significant result. I wouldn't have. It's not something that you would expect. So the fact that there's a theorem backing it is pretty significant. I think that's pretty cool. Okay, so now we're going to talk about Euler paths and circuits and Hamilton paths and circuits. And so an Euler circuit. So in both cases, a circuit is just where you end up at the same place that you started, right? But Euler was interested in consuming edges, and Hamilton was interested in consuming vertices. So an Euler circuit is a graph, in some graph G, is a simple circuit containing every edge of G, right? So you will have crossed every possible path. And so if you think about testing like an electrical circuit or something like that, then an Euler circuit, as far as testing, would mean that you've run your current through every possible point or every possible bridge or whatever in your electrical circuit, and you know that there is no disconnect. There's nothing broken. The current was able to complete the loop and it arrived back, and so the fact that it arrived back at the origin meant that your circuit is intact, right? And so you can think of Euler circuits in that regard, or if you think of them as bridges between different points or islands or whatever, then it means that you've walked over every bridge in this particular graph, right? And so an Euler path is a simple path containing every edge of G, right? So in this regard, you don't have to end up where you started, but you do still have to consume every edge, right? And so Euler was concerned with edges, Hamilton was concerned with vertices. So just keep that in mind as you go. Okay, so we have a new theory. A connected multigraph, and remember, a multigraph is a graph where you can have multiple edges between the same two vertices. So like an interstate and county roads connecting two cities, right? A connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. Okay, and so this is an interesting thing to think about. So the multigraph, right? Like you have multiple edges connecting the same two vertices potentially, right? And so this says that you're able to achieve the Euler circuit where you end up where you started, but you visited every edge in the graph, right? Only if each of the vertices in the graph has an even degree. And so what that means is that in order to achieve this, each time you go to a vertex, you need to be able to leave that vertex, right? Otherwise, you're stranded, you're marooned, right? And so you're consuming unique edges. You're only consuming the edges once, and once it's done, it's burned, right? So if you want to think of it as bridges, that it's burning the bridge each time you cross it, right? And so are you able to burn every bridge in your graph in a single pass and end up back where you started? And once it's on fire, you can't go back, right? Anyway, so in order to do this, right, in order to efficiently burn every bridge possible, you need a way out each time you enter a new island. And so you have 1 degree for when you entered the island, and then you have another degree for whenever you left it, or vertex if you want to say that, right? So in order to enter and to leave, you need 2 edges, right? And so if you enforce that requirement every time you visit a vertex, right, you need to be able to enter it and leave it, then you're always visiting vertices that have increments of 2, increments in degree by 2, right? And so it's because you have to be able to enter and leave, right? And so that's the requirement for an Euler circuit, is that all of the vertices have to have even degree, and it makes sense when you think of it in that context. Okay. So another theory, a connected multigraph has an Euler path but not an Euler circuit if and only if it has exactly 2 vertices of odd degree. And it's for that same reason. So in that case, the first and the last vertices would be the ones with the odd degree. And all of the others, like in order to achieve an Euler path, you have to consume every edge, you have to burn every bridge, whatever analogy you want to use whenever you're discussing this, right? And so for that first vertex, whenever you leave, then you have degree 1, right? And then if you visit it subsequently, then you're doing it in increments of 2, because you're entering and then leaving, by different edges each time, right? So that keeps it odd. And then whenever you end up at some spot, and so you're just entering, right? And then any other times you visited, you would have entered and left, so that you would have some odd degree for that last one as well. And so those are the 2 theorems for requirements on circuits and paths for Euler's circuits and paths. Okay, so now we define a Hamilton path and a Hamilton circuit. So a simple path in a graph G that passes through every vertex exactly once is called a Hamilton path. And a simple circuit in a graph that passes through every vertex exactly once is called a Hamilton circuit, right? And so in this case, we're visiting every vertex once. And so for a path, we don't have to end up where we started, we just visited everyone once. And for a circuit, we do. Right? And again, this is vertices, as opposed to where Euler was concerned with edges. Okay, so Dirac has a theorem on Hamilton circuits. So a simple graph with n vertices where we have more than 3 or more nodes, such that the degree of every vertex in G is at least the ratio of n over 2, so that for every 2 vertices in the graph, the degree of every vertex in the graph is increased by 1. Right? So to support the ability to create a Hamilton circuit, you have to increase it at a rate of 1 out of 2, and no less. Right? So that this requirement would be for a graph with 6 vertices, then you would need at least degree 3 for every vertex. For 7, you would have to use a ceiling function, and then you would have degree 4 for every vertex in order to guarantee a Hamilton circuit. And so this isn't if and only if, it's if then, right? So if you meet this requirement, then you have a Hamilton circuit, but it's always possible to have a Hamilton circuit where every vertex has degree 2, and it's just a ring or a circle, right? So you just have this big loop. So that possibility always exists, but to guarantee a Hamilton circuit, and you don't have that other guarantee, then this is a requirement. And then there's this alternative one that says so this is Orr's theorem. If G is a simple graph with n vertices, n greater than or equal to 3, such that degree u plus degree v is greater than or equal to n, then for every pair of non-adjacent vertices, u and v in G, then G has a Hamilton circuit. Okay, so what is this saying? It's saying, okay, well, you can relax this requirement that all of the vertices have to be greater than or equal to n over 2, right? Or have degree greater than or equal to n over 2, so long as you meet this alternative requirement. And what this basically says is that, because it's requiring, for every non-adjacent pair u and v or whatever, because it's requiring this, it's saying that they have to average, every pair of non-adjacent vertices in the graph has to average a degree of n over 2, which basically says that you can have one exception so long as every other vertex compensates for it by getting the sum of the least connected vertex with every other vertex to be greater than or equal to n, right? So you can have one exception so long as every other one compensates for it, and you meet this alternative requirement. Okay. Okay, so shortest path, and we're going to be spending, let me see, yeah, we're going to be spending basically the rest of the time talking about Dijkstra, right? And then, I will send you on your way. Okay, so graphs that have a number of assigned to each edge are called weighted graphs. And so you can think of this in terms of the highway analogy as being like the miles for the road, like the edge between Dallas and Austin has on I-35 has a fixed number of miles, and so that can be the weight. Alternatively, the weight can be described in terms of gallons per edge, right? So the weight for taking some pickup truck versus some hybrid car in terms of the number of gallons of gasoline consumed while traveling from Dallas to Austin will be different as well, right? So it's not necessarily miles in terms of the road. You can use gallons consumed by vehicle for that stretch of road, and then that would be an alternative measure of weight. Right? Okay, so those are weighted graphs. It's where the edges have a weight associated to them. Let the length of a path in a weighted graph be the sum of the weights of the edges of this path. Okay, so if you're using miles, then the trip from Dallas to Detroit has a length in terms of miles, and it's not the radial distance. As the crow flies, it's the sum of the miles traveled on the roads that got you there, right? So that's all we're saying here, and so the length is just that length, right? Right. So this is corresponds to our intuition of the length of a road trip. Right? Okay. So then, in theory, Dijkstra's algorithm finds the length of a shortest path between two vertices in a connected, simple, undirected weighted graph. So Dijkstra's algorithm is provided on page 747 of the book, and I've kind of given you an outline here in Java of the objects you'll have to create. You need a vertex, you need an edge, you need a graph, and the graph is actually missing the solve function, and we'll discuss that in a second. And then you need some main function to set it all up, right? And so this kind of initializes the graph. And so, let's see, what else do we have? Like planar graphs. Yeah, we're not really going to discuss planar graphs at the moment. And then graph coloring. Yeah, so we'll skip that for now. If there's time, we'll talk about it before the end of the semester. Okay, so Dijkstra's algorithm uses big O of n squared operations, right? So it's a loop within a loop. You should think that anytime you see n squared. Define the length of a shortest path between two vertices in a connected, simple, undirected, weighted graph with n vertices. We'll discuss that in a second. And then the traveling salesperson problem is, it's a Hamilton circuit of shortest length, right? So a traveling salesperson wants to visit each of n cities exactly once and return to their starting point. That is, they wish to find a Hamilton circuit of a simple, complete graph of minimum total weight. And then, so this is different than Dijkstra's algorithm, where we're finding the shortest distance between two distinct vertices. Like in this case, we want, in the traveling salesperson problem, we want to visit every vertex once, and we want to do it with the minimum cost. Right. Okay, so then we're skipping planar graphs right now because I don't particularly have anything interesting to say on them at the moment, and so we'll come back to Dijkstra. Okay, so Dijkstra is sufficiently complex that I want to visit it separately, and so I've given you a bit of an overview in terms of the files you'll need to create it in Java, and now I'm going to show it to you, and I'll provide you with the JavaScript file, but I'm going to show it to you in JavaScript, and then we're going to run it using Node, and you'll see, you'll learn a little bit of new syntax in regard to JavaScript, and the basic JavaScript, like raw JavaScript or ECMA script, doesn't exactly define a class, but it does have the concept of constructors, right? And so you can kind of wedge your way into something that looks like a class. Sorry, let me see if I can zoom this in. Yeah, I really should have considered that. So I will provide this file to you on e-learning, so you can follow along on your own computer as we review it. I'm sorry that I don't have the the know-how to increase the resolution just this moment. Anyway, so what I was going to say is that the bonus problem for your second exam will be to implement Dijkstra's algorithm, and I will give you I'll give you the edges and the vertices, similar to how I'm going to show you here, for that. And I'm going to ask you to write your solution in a way that can be tested on Rex Tester, so the same way that I asked you to do it for the first exam. And you'll be using either Java or C#. It'll be your choice. But I'm going to ask you to implement Dijkstra. I will give you the vertices and the edges, and then we'll test it and make sure that your solution works. And that'll be your bonus problem for the next exam. So you have some time to work over it. You have some examples. You'll be translating from JavaScript. But yeah, it's time that we start getting into code. So okay, so we're going to use Node to test this. So previously we've used the interpreter that came with Chrome, but now we're going to use the desktop application, and we'll use Node. So we can look at this as a translation of what we're doing in Java. So we have a Vertex class, and it has these private variables. It has a name, right? And it has an array of edges, okay? And then we define get name here, right? Because in Java and C# we'll define getters and setters, these access methods to get private variables without letting the outside world get at them. And so we could do a little extra work in JavaScript to make them private, but for now I'm going to assume that y'all aren't terribly familiar with JavaScript, and so we'll just start at the beginning, right? So functions, it's time that I was also a little bit honest with you about JavaScript. JavaScript's weird. If you're coming from C or Java or C# or almost any other traditional language that they would teach at UTD, JavaScript's going to be a little bit weird, and I still say it's worth it, but you do have to learn how to use it wisely, because it's very easy to write really bad JavaScript, and so hopefully you'll at least get a little bit of introduction in this class and in what's available, and hopefully we'll maximize the good and minimize the bad, but I can make no guarantees on that. Failure is always a possibility. Okay, so we want to define a class, but the closest we can do is define a constructor, right? So in Java and C#, the constructor is always going to have the same name as the class, and so our JavaScript prototype is going to have the same name as what we wish we could name our class, right? So in this case we're naming it Vertex. We're assigning it the value of a function, and so in the same way that whenever we instantiate a vertex we would call new vertex, whenever we do that here, we are still calling new vertex and we're passing an item into the constructor, right? And then we're going to get an instance of a vertex back whenever we do that. So this is in very real effect a constructor, and this is kind of a placeholder for our class. And so the instance methods, right? So add edge, instead of being able to stick it here inside this function definition, the appropriate way to do it in JavaScript, with raw JavaScript, and we'll get into TypeScript, and we'll get into, if we have time, we'll get into React and Angular and maybe Vue, but probably just React and Angular. And so the way to define an instance method in raw JavaScript is, once you have your constructor, to define a prototype, and it is also a function, so we're assigning that to this function, right? So this is the way to do this in JavaScript, and so we're adding an edge here, and so we just push the edge here, right? And so then we also want a toString method, right? We have that. So here we have a toString method, so it's nice if we have a toString method for our vertex. So we implement that. I am a huge fan of interpolated strings, so you'll see that all the time. So that's why I have these backticks and stuff. Okay, and so we could do the same thing for edge, right? Like we could define a constructor and then add our toString method on top of it. But I'm going to show you an alternative way to do it, and then I'll discuss the differences a little bit. Okay, so edge would have been our next object, right? And so we have name, a source vertex, a destination vertex, and a weight, right? And so we have the getters for those, and then the toString method. And then the next object would be the graph itself, and the graph is a combination. It's a pairing of vertices with edges, right? And so we've discussed that in the definition of a graph. And then we've also given it a name to identify the graph in case we have multiple graphs. Okay, so graph we define with a constructor in the same way we did the vertex. And then we add instance methods, add vertex, which we're given a vertex ID, and we create a new vertex instance and we add it to the graph, right? And then we have a connect vertices instance method, which takes a source ID and a destination ID and a weight. And so this is essentially like a make edge function. And so we're connecting the two vertices. And so they have to be previously defined, otherwise this isn't going to work. And so you create the vertices first, and then you start connecting them, connect the dots basically. And so you have your source, and so this is a vertex at this point, right? Because it's vertices that are stored as the value of our map, right? So it's key value, right? So the key is going to be the name of the vertex, and the value will be the vertex instance. Right? So we have our source vertex and our destination vertex, which we retrieved using our source ID and our destination ID. Okay, and then the edges, we also want them to be key value, but because Dijkstra deals with undirected graphs, or actually I guess you could use Dijkstra on directed graphs, but we're going to consider undirected graphs for now. And then I'll leave it to you to think about how you would modify this to handle directed graphs. But the edges, because we want symmetry, because we want to deal with an undirected graph, then the weight is the same going from source to destination as if we reversed it and went from destination to source. And so I have this forward key where we use source and destination as they're passed in, and reverse, or I could have called it, symmetric or whatever, where we flip them and we go from destination to source. And it's just to show that the edge goes in both directions. And so here, right, we didn't create an edge constructor the way we did for graph and the way we did for vertex. Here I'm using the new JSON, so the JSON object notation, and so we're creating a JavaScript object, right, or JavaScript object notation, sorry. And so we're creating a new object, and just like we had these properties that went with the instance of graph here, we can have these properties here, and its key value pair is essentially the same as if you would have for a class. And then we can also have instance methods in the same way, where we can use this, like we're using the this keyword everywhere else, and it'll bind it to this JavaScript object. So what's the difference? Well, if we change the definition of one of these instance methods, and we're using the prototype method, where we use the constructor and then we instantiate it with the new keyword, then we only have to change it once. Whereas if we use this, then we have to chase down every instance of edge and overwrite its implementation of toString. And so it, if the code is static, then it's all the same, right? But if you're making updates or whatever, then or if you're relying on some closure or whatever, then it could potentially be different. But I'm just showing that there is an alternative. So if as I tell you, JavaScript is weird, and you find defining stuff on the prototype for a constructor method, right? So you don't like using this, you really miss having classes, and you want something that resembles it a little more, then perhaps this notation is really more to your liking. You can still use the this keyword, and you'll get basically all of the same stuff. So it's fine. You can go either way. I just wanted to introduce you to both concepts. Okay. And so I'm not sure if you're going to be able to hear me. There's a bunch of stuff going on outside my house. Anyway, yeah, I don't know if that's picking it up. Okay, so then I distinguish between printable edges because I want to be able to, I like toString functions. I feel like you should be able to have some console-friendly version of whatever data you're looking at, whatever data is in memory. You should be able to print it out to the screen so that you can see what you're dealing with, like how everything's configured. Okay, so I have these printable edges because, again, we're only adding one edge, but because I want this symmetry property, I want it to be the same whichever ID you pass in first, and you'll see where that's convenient in a minute. I want that edge defined the same edge, right? The same edge, but where you can use it in either order, right? So the edge connects, node A to node B. It also connects B to A, and so I want you to be able to pass it in either order and get the same edge, right? So we've defined the key forward and backward, and we add that edge for both keys, so you can look it up either way. But to make sure that whenever we're printing it, again, because I insist that we be able to print our data to the screen, I have this additional one, and so this is just for printing, right? So it's printable edges. Okay, and then the source vertex, just for convenience, it should have its own reference for the edges that it's connected, that are connecting it to other nodes. And the same with the destination. Anytime it's connected to some other vertex, it should have some reference to it on its own so that it can look up its neighbors, right? So that's what we're doing here, and we defined add edge earlier. Okay, so now we have get edge, and we want a convenience method that will build these strings for us, right? So it'll create the key and look it up for us using source and destination, right? And so it directly references the edges because it's an instance method. It's defined on the prototype, right? So it's an instance method. And so it'll look it up or it'll return null if it doesn't exist. Okay, so we'll come back to Dijkstra in a second. And then this is the print function. And so print is similar to toString. You can call it whatever you want, except I'm not returning a string, and toString should be the string representation returned from the function. I'm asking it to do a thing. I want it to print it directly to the console. I don't want to get a string back. I want it to do the printing. And so because I'm using the console logs, right, or in C# it would be console.writeLine. In Java it would be system.println or something like that. I forget what it is. System.out.println, maybe something like that. Anyway, so this will go through and it prints out the vertices, right? So it gets the vertices and it changes the hash map or the dictionary into an array, and then it iterates over the array, calls a toString method for each one while printing it to the console, and then it lists the edges and does the same thing. It takes the dictionary, the printable edges, converts it to an array, iterates over the array, and writes that data to the console. And so down here you'll see the two instances of graphs that we're going to look at. Okay, and then solve Dijkstra. So this is the instance method defined on the graph that we use Dijkstra's algorithm to go from some point of origin to some terminal vertex, right? And so this is the code implementation of the algorithm that's listed in the book. So you can see that JavaScript does define an infinity, right? And so just as the algorithm in the book recommends, we define infinity. We have some lookup, and it keeps track of both the path and the weight, like the shortest distance to that vertex, right? And so all of this is relative to this point of origin, right? So all of these distances are measured from wherever you say your starting point is. So if your starting point is Dallas, then that would be your point of origin. And then everything that we consider would be the shortest route to get from Dallas to that other city, right? And so it's not exhaustive. This, Dijkstra's algorithm doesn't return the full matrix of shortest paths from city to city and what that path is. It takes a look at a specific example. You start here and you're going here, and then it builds up by looking at all of the adjacent vertices, so to your original vertex. So you start at Dallas, and then you look at all of the adjacent cities. So Austin, Houston, Oklahoma City, wherever else. And then if you're going to Detroit, it then looks at, well, okay, so we have all of these other cities, and we have the shortest path to get there from Dallas is to go straight there, not to go to Miami, Florida, and then back to Oklahoma City or wherever. The shortest path is to go directly there, and so that vertex has already been solved. And so then we look at that, and we look at all of the cities that Oklahoma City connects to, and we ignore the ones that have already been solved, right, that are stored here. And at this point, after one iteration, the only one that would have been solved would have been the point of origin. Right? Okay, so let's take a look at it real quick, and then, but I'm going to leave most of this to you to look up on your own. You have it, in fact, let's just do that, right? So you have the pseudocode, right? And it explains the gist of the algorithm, and you have an actual implementation of it. And so I'll show you how to run it, and then I'll leave it to you, right? Because this is going to be your bonus problem, so I don't want to get too far into it. But essentially, you initialize everything to say, well, it's infinitely far. And you say, well, except for that first vertex, that one is definitely finite. It's distance 0, and it just has that one vertex, right? And so we have the solved dictionary, or we're using it as a list, and a list of unsolved ones. And the unsolved is a copy of all of the vertices, right? And so then we move, we define this get next vertex, and that finds us the shortest distance to a node that isn't solved, right? Yeah, there's some optimizations that could be made here, whatever. So we define this, and we're going to use it here inside our loop. And so we say, while the terminal vertex we haven't determined the shortest path to our terminal vertex, then we're going to call this get next vertex, right? So get the next shortest path to a city that we have established. And then if it's null, so if we've exhausted the list and we still haven't solved our terminal vertex, then there's some disconnect in the graph, like it's just unreachable, right? So that's when you would get null. So break out of the loop, you didn't have a solution, it's infinitely far, or whatever. And so otherwise, then the next vertex has been established to have the shortest path to that particular vertex or that city or whatever, right? So we've solved it to that vertex, but we're trying to get to the terminal vertex. So then we move it, we add it to solve, we removed it from unsolved, and then for debugging purposes, we're logging all of this stuff. You can comment it out if it's too noisy. And then we loop through all of the unsolved nodes, and we look at the edges for those. And so then we see if there's an edge between the current vertex, right? So the one that is the most recently solved vertex, and just this whatever next unsolved node we're considering. And if there is an edge, if they're connected, and if the distance between the point of origin, right, and this latest this new node is less than whatever the shortest distance to date for that path is, or not necessarily the path, but the shortest distance to date from A to X, right, from your point of origin to whatever one you're considering, is then you have some new shortest distance for that particular node, right, for whatever is at key. So then we update our lookup, right, and then we just do that in a loop. And once we've done that, so essentially once we've looked at all of the unsolved nodes that are connected to our most recently solved vertex, then we will have a new solved vertex. Like each time we complete this inner loop, we have a new solved vertex, right? And so then we go back and we see, well, first of all, have we solved our terminal vertex? And if not, then run through it again. And then once we exit the loop, we either will have failed to solve it or we will have solved it. So here, you can uncomment this. And you run it by calling node and then the name of the function, or the name of the file, right? And it'll give you all of the debug information. So the first thing it'll do is it'll print out your vertices, your edges. And so the vertices will have the degree, the edges will have the weight and source and destination. And then this is all debug stuff. And then the last thing it'll print out is the shortest path from whatever you were looking for, right? So we were looking for A to D. Okay? So it gives you the shortest path, tells you the vertices, and then it tells you the weight. Okay? And so I have two examples. The first one is something that I constructed, and the second one is the example that's in the book. And you run it the same way, and then it gives you the shortest path, right? Okay, so I'll include this on e-learning, and take a look at it. Get to work on trying to reproduce it in Java or C#, whatever language you're more familiar with. And have a good evening. We'll talk on Thursday.